Okay, so this is our first problem. So going further, we're going to talk about the continuity equation in terms of partial differential equations. Okay, so this equation, these equations, the first equation, the second, and the third. The first equation represents the continuity equation in a three-dimensional incompressible fluid flow. The second represents the continuity equation in a two-dimensional incompressible fluid flow, and the last in a unidimensional flow. So we can use the continuity equation to confirm the possibility of a flow if you know the velocity components. For a three-dimension, you should have three velocities: one along the x-axis, another one along the y-axis, and the other one along the z-axis. For a two-dimensional flow, you should have at least two velocity components, one along the x, another one along the y. For a one-dimensional flow, you should have at least one velocity. You should have one velocity component, okay, in the x direction or in the y direction or in the z direction. So if you're given a velocity component and you differentiate it with respect to a particular direction and you get a zero, it shows that the flow or the mass is conserved, or the law of conservation of mass has been upheld, and therefore the flow is physically possible. For example, if you're in this example, let me read it. In a three-dimensional incompressible fluid flow, this is supposed to be fluid flow, the velocity components in x and y directions are u given by x squared plus y squared times z to the power 3. And the velocity component along the y v is given by negative xy plus yz plus zx. Use the continuity equation to evaluate an expression for the velocity component w in the z direction. Or in other words, find the other velocity component in the z direction. We've been given the velocity component for u and for v, and this is a three-dimensional incompressible flow. So find the other velocity component. So how do you do that? You write solution. You write the formula for the continuity equation. It is given by the partial derivative of the velocity component along the x direction plus the partial derivative of the velocity component along the y plus the partial derivative of the velocity component along the z, then equate them to 0. Because the continuity equation is equal to 0. Then find this derivative of u with respect to x or v with respect to y. We do not have the v, okay? We don't have v, so we're looking for v. So when you find the first component and the first term and the second term, substitute in the equation. So how do you find the first term? Differentiate the given velocity component here, this one, with respect to x. So how do you differentiate that? You concentrate on the variable which is given down here. So in our case, the variable is x. Differentiating it, you're going to get this coefficient, the power, its power, and multiply it with the coefficient of the variable. The coefficient in this case, it is 1. So it will be 2 times 1 to be 2. And then reduce the power of the variable by 1 unit. So 2 minus 1 is 1. That's why x here is to the power 1. Because you have reduced the exponent by 1. So and then y squared and z to the power 3 will act as constants because we are only differentiating with respect to one variable, which in this case is x. So this first term here is equal to 2x. Second term, we're going to differentiate the velocity component along the y with respect to y only. Okay, because it is the y which is appearing here. Differentiating that, we do the same here. The first term in the velocity component along the y-axis, the first term has power, which is has power 1. I'm looking at y right now. It has got power 1. So that 1 times the coefficient of y to be just 1x. Okay? Then reduce the power of y by 1. It will be y to the power 0. So to be just 1. And that's why here you are seeing just x appearing only. Here, only x is appearing. Also, we have a y here. Different. Do the same thing. Reduce the power of y by 1. Also multiply the power of y, which is 1, by the coefficient of y, which is still a 1. Here you will remain with z only, because y to the power 0 will be a 1. That's why we have a z only here. Okay, so now you have found the first and the second term. Substitute them in the equation. You obtain 2x minus x plus z plus the partial derivative of w, or the partial derivative of or with respect to the partial derivative of z. So we are looking for w. Make this derivative the subject. Okay, we are going to have this derivative will be equal to z minus x, but this is a derivative with respect to x. So you do what is known as antiderivative or antiderivative, which is integration. So since this is a derivative with respect to z, you are going to do the antiderivative with respect to z, or you're going to integrate it with respect to z. Doing that, remember this is representing the change of this velocity according to, with respect to the change in the z direction. So the opposite of that is to, the opposite of changing is what? Is to take away the change, isn't it? So the change will go away. So we'll remain with w should be equal to, then this will be integrated with respect to z, and this one with respect to z. So let's look at the second term first. Integrating this with respect to z. So here z is to the power 0. Okay? Here z is to the power 0. We are going to increase the powers of z and then dividing by the new increased power of z. So x z to the power 0 plus 1. So it will be now z to the power 1, and that's why the z is appearing. Then divide by that 1. You remain with the same thing here. Integrating this term with respect to z, increase here the power of z is 1, so increase it by 1 to become squared. Then divide by the same new power that you obtain, that is the 2 that we have there. Then plus a constant. A constant can be arbitrary, can be a function of xy, can be a number, or it can really be a 0. So this is your velocity component w along the z direction. Substituting, assuming that the constant is a function of x and y, because that is the best assumption that you can make. You end up with w being equal to negative xy plus z squared plus fxy. This is the velocity component along the z direction. Using the continuity equation to obtain the missing velocity component. Another example number 8. Given the velocity component along the x by this expression and along the z by this expression, what is the most general form of v, which is the velocity component along the y, so that the flow is possible for a steady 3-dimensional compressible flow? So we know that when we find the derivative of u of the velocity component that we are given with respect to x, there's no x here. Okay, so derivative will be 0. When you find the derivative of w with respect to z, there's no z here to be reduced. The velocity or to change, the velocity will be equal to 0. So the only way the three components, the first, the second, and the third component can be all equal to 0 is when even the third component is also equal to 0. So that's why we're saying that also the rate of change of this velocity with respect to the y direction must be equal to 0. Then integrating this, you get a constant or a function of x and y such that if you differentiate it, you still get if you differentiate it with respect to y, which is not in the function, which is not one of the variables for this function, you get a 0. And that's why we have that. So those are the two examples. Maybe we can try to discuss them. We can try to ask around those examples before we go further. Yes, class.
Yeah, I see.
Hello.
Yeah, I just want to the clarity. What is the reason why we integrate? From the top there, the equation is okay, but I don't understand why do we integrate those values after we differentiate.
From oh, you can open your mic. Is it from at this? You're talking about this point. Are you talking about this point?
I'm I'm saying in both equations, the ones you give solutions, everything from top is okay.
Mhm.
But you see in this equation, you explained u dz is equals to 0. Yes, dw dz is equals to 0. But
Yes.
then you say upon integration with respect to z. What is the essence of this one? Where is this integration coming from?
Upon integration with respect to z. Okay.
Yeah.
Let 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 let,
Say
let me
what
make
is asking from the
before you ask.
page 6.
Before you ask. Let me go on the right screen. Are you talking about this screen?
No, from the previous solution number 7. Yeah, that one.
This one.
When you finished the substitution, you said substituting these values in the continuity equation. We got integrate what. Then you said upon integration. That
Mhm.
part. That's what is.
Before I answer, am I on the right screen? Are you talking about this screen? Example number 8.
Yeah, in both equation, no problem, even example 7 or example 8. But my issue is it comes on integration. This part of integration.
Okay, I think I'll go to example number 7 because it is less trivial. So I'll go. So now let's look at we're at this point, okay? So from here, I'm saying we integrate. Why are we integrating? That is your question. This is saying the rate of change of W with respect to Z. This is not W, this is the rate of change of W. Okay? So for you to find W, you must integrate or you must carry out a process known as an antiderivative so that you find the actual W here.
Okay, okay, I understand. Thank you.
Yeah. So I find the actual W. So next now we're going to talk about the velocity potential and stream functions. So these are relationships that relate to the velocity, and we can use them to determine a lot of things, and we can write them in different forms. So now the velocity potential is a scalar function of space and time such that its negative derivative with respect to any direction gives the fluid velocity in that direction, and it is given by this symbol phi, okay, or phi. So the velocity potential, for example, for an unsteady three-dimensional fluid flow, remember unsteady, it has to depend on what? The velocity variable, the flow variables has to depend on what? On time. For steady one, the flow variables don't depend on time, they only depend on space. So if you're given a velocity potential like this, you can determine the velocity components depending on the derivative that you've decided to differentiate the velocity potential with. So if you differentiate the velocity potential with respect to the x direction, so the negative derivative of the velocity potential in the x direction gives the actual velocity of the fluid in that direction. So for x-axis, for the x variable, we're talking about the velocity along the x-axis. For the y variable, we're talking about the velocity along the y-axis, and for the z variable, we're talking about determining the velocity of the fluid along the z direction using the velocity potential. But remember, when you have u, v, and w, you can substitute the u, the v, and the w in the continuity equation, and you obtain this equation here. So substitute your u and your w, your u, your v, and your w in the continuity equation. You can this means that you are differentiating now second derivative of your velocity potential, second derivative with respect to y or your velocity potential, and that's why we're having a 2 here, okay, and the 2 down here to represent the second derivatives. And then when you evaluate this, you get this equation. This is known as the famous Laplace equation. And with the Laplace equation, we can use it to determine whether the fluid is incompressible, rotational, or even the possibility of the fluid flow. Because this is actually the continuity equation. That's why we can a continuity equation for an incompressible fluid, and that's how we can use it to determine the possibility of the fluid to flow, because it is satisfying the continuity equation. Then apart from that, there is what is known as equipotential, an equipotential line. So at an equipotential line, the velocity potential is equal to 0, or the rate, not equal to 0, is a constant, and the rate of a constant is always equal to 0. It's an equipotential line, the velocity potential is constant, and its derivative, d phi, is equal to 0. But we are saying that we can write the velocity potential for a two-dimensional flow as a difference equation. This is our difference equation. This is our derivative. You are differentiating this with respect to, first of all, x direction plus the y direction. But remember, phi x derivative, this part here, this section of the term, is equal to the negative velocity in the x direction. Then this section also is equal to the negative velocity in the y direction, because we're differentiating with respect to a y. And then substituting these negative u and negative v back into this equation, you're going to obtain this equation here. Then factorizing the negative, you end up with u dx plus v dy, which is still a difference equation. But remember, we said that the velocity potential is constant at an equipotential line, and its derivative is equal to 0. So it means that we can equate this section to a 0 here. because this phi is a 0. So we can equate it to 0, and then the negative can be divided out. You obtain this equation, and then we can make dy dx the subtotal formula to obtain the last equation here. So what does this equation tell us? We can find which is the slope of the equipotential line. We can determine the slope of the equipotential line by, if we're given two velocity components using this equation at the end here. We can determine the slope of the equipotential line using these two, if we're given two velocity components using this equation. Do you have an example for this? No, we don't have. Yeah. The next one is the stream function. So there is a velocity potential and the stream function. So for a stream function, unlike velocity potential, is defined as function of space and time such that its derivative with respect to any direction gives the velocity component at right angle to this direction, at right angle to this direction. So if I differentiate this stream function with respect to x, okay, I'm going to obtain the velocity at right angle to the x direction, which is the velocity along the y. The same if I differentiate this stream function with respect to y, I'm going to obtain the velocity right angle to the y direction, which is the velocity along the x axis. We can also substitute it in the continuity equation, and then you obtain this equation here, the equation at the bottom here, because our u and our v have been found using the stream function. So, and then differentiating this further, you obtain these derivatives here. So there's a relationship between the stream function and the velocity potential, and this is the relationship between the stream function and velocity potential. Since both of them, you can use both of them to find the velocity components. So you can just see how you can try to relate those velocity components according to the relationship that we defined up there. So this is how the velocity potential, this one, is related to the stream function. Okay, not the variable c. This is with respect to y, sorry, to x. Then this one is with respect to y. If you want to find the velocity components along the y direction, if you're given any one of them, make sure you differentiate them with respect according to the way they are related. This is with respect to y, and then this is with respect to x. And then there are also signs. This is negative, this is positive, this is negative, that is positive. An example, determine whether the following function presents a possible irrotational flow. So a possible irrotational flow, just try to see if this stream function is going to satisfy the continuity equation. That's all. Try to see if this stream function is going to satisfy the continuity equation. So how do you do that? Remember, what is the relationship? Okay, this equation here, we're going to use this equation. Okay, differentiate it, find the second derivatives of the stream function. Find the second derivative of the stream function. So the first derivative, differentiate this with respect to x. For the x direction, you're going to differentiate x, okay, which is going to give you 2x, but there's an a here, we're going to get 2ax. The y is constant, so it will be a 0. Differentiate also here with respect to y, The x will act as a constant, so it will be 0. Then find the derivative of this variable, you're going to get -2. There's an a here outside, so 2 times -2. This is -2ay we are obtaining. The next one is to find the second derivative by differentiating this one, okay, once more, which is represented by this symbol here, second derivative. So differentiate this one with respect to x. The x here is to the power 1, so the 1 will reduce, and then it will be x to the power 0, which is just a 1. Then 1 times this coefficient, which is 2a, it will be just a 2a. The other one, differentiate now this one second time with respect to y. That's why we have y2 here, y to the power 2 here, y to the power 2 here. Differentiating this, the y is to the power 1, so the 1 will reduce to y to the power 0, and number to the power 0 is 1. 1 times this, it will be -2a. Then substitute in the continuity equation here, okay, you find that this is 2a minus -2a, you get a 0. Since the continuity equation has been satisfied, therefore the flow is physically possible for an irrotational. The irrotational fluid flow is physically possible. That's the implication. So anything to say about that? Anything? Any questions? Any questions, class?
No questions, sir, but I guess we need this module for revision, because now we are just seeing it on the screen.
Oh,
No,
okay. I'll post it on. I'll give it to you. I'll give it to you. The same module I was using the last time.
Yeah, because if you give us this module, we can also go through after this lesson. We can go through and see what is happening, because it's only an issue of differentiation, double differentiation there. So we need to go and see what is happening.
Okay. So that you even practice, you even write. Yes, I'll do so. I'll quickly do so after the class, immediately after the class. So the next, this is another example. The example is saying that the velocity components in the fluid flow are given by this. We have two velocity components, u and v. Show that the flow is possible. Derive the relative stream function. So to show that the flow is possible, we got the continuity equation. This is the two-dimensional flow because it only has the x and y components, velocity components. So go write a continuity equation for a two-dimensional flow. Let me just jump back to the continuity equation for a two-dimensional flow. This one. This is this one here. So this is the continuity equation for a two-dimensional flow. So substitute, find the derivatives of those given velocity components and substitute in this equation. If you obtain a 0, then the flow is physically possible. If not, it is not physically possible. Where is the equation? This is the question. Yes. So find your derivative of u with respect to x. This is your u. So differentiate it with respect to x, you're going to have dy. Then your y also differentiate it with respect to x, to y, sorry. Your velocity along the y, differentiate it with respect to y. The first term here is a constant, it will be 0. The second term is x, it will be as though it were a constant because we are looking for a derivative with respect to y, or the change along the y direction. So this will be a 0 because the change in the x will be 0 for this one. Then the change along the y direction will be the derivative of this y variable here, which is negative 2y. Then substitute these two into this equation. Derivative of u with respect to x, which is 2y, plus derivative of v with respect to y, which is negative 2y, gives us 0. The continuity equation for steady incompressible flow is satisfied, and therefore the flow is physically possible. If you found any other number apart from 0 or anything else apart from 0, then your conclusion was going to be that the flow is not physically possible. Okay? Then find the relative stream functions. You first go to the relationship between the velocity component and the stream function. And the relationship is that the velocity component for a y direction, for the x direction, is given by derivative of the stream function with respect to the y direction. Okay, remember there's a velocity potential and there's also stream function. Remember how they relate to the velocity. So we know that the velocity u is equal to 2xy. Okay, the velocity u is equal to 2xy. So we need to find this stream function. But this expression here is showing that this is the rate of change of the stream function with respect to y. So integrate it to get the actual stream function. Okay, the actual stream function psi will be equal to integral of this side, or what is this side, okay, with respect to the variable which is down here, in this case dy. Okay, integrate 2xy with respect to y dy. So integrating this with respect to y, you are increasing the powers of y, then divide by whatever new power that you obtain. So if it's y to the power 1, increasing the power by 1, you're going to get y squared over y power 2 over a 2. But there's a 2 in front already here. So the 2 and the new 2 at the bottom will cancel. Plus, we would have written a constant, but the reason why we're not writing a constant is that even a function of x can act as a constant when you differentiate the stream function with respect to y. So we're saying maybe the other number which was there could have been a function of x. Who knows? And that's why we're writing f of x here instead of a constant like c or k. Okay, but we know that the stream function is also related to the velocity component along the y by this relationship. Okay, will be equal to, if you differentiate this one with respect to x this time around, okay, we are differentiating this with respect to x. Your x, which is x to the power 1 here, will go remaining with y squared only, plus differentiate this function of x we introduced with respect to x to be just f prime. F prime is the same as differentiating this function with respect to x. So this must be equal to the velocity component, which we already have, we've been given already, along the y-axis, which is a squared plus x squared minus y squared. So by equating this and the last part here, so we're looking for this function, like what is it, what is this function of x here? Okay, that's what we're trying to do with this here when we differentiate this. So making this derivative the subject of the formula and then integrating it, you get an f. So you're integrating each component with respect to x. So a squared is a constant, there's no x here, or the x is to the power 0. When you integrate it, to be x to the power 1, and that's why we have an x here, and a squared x plus the x here is to the power 2. Increase the power by 1, divided by the new increase. So 2 increased by 1, you're going to get x to the power 3 over the new power, which is the 3 here, minus this x here, minus this y squared here. We are integrating with respect to x. So the x here is to the power 0, so to increase by 1 to be x to the power 1. Then the y squared is maintained. Plus now a constant. Now this constant, we cannot say it could be a function of y. No, because we're already coming from a function of y. So we cannot say it could be a function of y. Because if it is a function of y, we're implying that this function will also be, we're implying that, no, the reason why it can't be a function of y is because we're already coming from a function of y. Yes, I think that is enough. And then substituting back this f into our equation here, we're going to have xy squared plus whatever you got plus a constant. Now this will be just a constant. So that is the last example for today. I don't know how long this class was, but the other class was very long. Yes, class. Any discussion around those derivatives?
I think if we could waive the module and some questions, we will do some practical.
Okay, I'll give you the module and I'll prepare a tutorial sheet on this with enough questions for you to practice.
Yeah, this one needs a lot of questions because it
And
needs a lot of understanding.
those questions, I'll try to find time to. We'll see how we'll discuss them. Yeah. And so I'll give you this module and I will also give you the tutorial sheets on the flow, on fluid flow. So this is the end of the class on fluid flows. We're almost saying goodbye to differential equations.
So this is the only part of questions on.
Yeah, this is the fluid flow, the topic fluid flow. We are done. We're done. The fluid flow topic, we are done with it. So I'll send you the module immediately after this class. Yeah. This time I won't forget this time around.